Good morning, everyone. We are Group 5, and today we are presenting our project on an adaptive cruise control system for a scale model vehicle. Our goal was to design a small car that can follow another vehicle at a safe distance using a control system based on real-world SCC principles. We'll briefly cover the problem, objectives, design, modeling, hardware, sensors, control algorithm, coding, and a demo of our working system. Let's start with the problem we aim to solve. In modern driving, maintaining a safe distance between vehicles is essential, especially in changing traffic conditions. Our goal is to design a system that lets a car automatically adjust its speed to keep a safe distance, set at 0.2 meters in our scale model. The car should slow down when too close, speed up when too far, and maintain speed when at the right distance. To do this, we developed an adaptive cruise control system using real-time distance sensing, dynamic modeling, and a PID controller to ensure smooth and responsive speed adjustment. Next, let's look at the objective for our project. Our main goal is to design an adaptive cruise control system that allows a small vehicle to autonomously follow a lead car, maintaining a safe 0.2 meter distance. To achieve this, we focus on 5 key areas: distance regulations, where speed adjusts based on real-time gap detection; feedback control, using sensor data to continuously fine-tune the vehicle response; dynamic modeling of the car's motions using physical parameters like mass and damping; PID control, ensuring smooth, stable speed changes without overshoot; and finally, validation through both simulation and real-world testing. Our aim is to replicate how actual SEC systems work, combining safety, accuracy, and efficiency in a scale, cost-effective setup.
Okay, I am raising. For now, I want to present the design specification for our project. The first one is the scope. Our auto car can maintain the cruise speed and also can automatically adjust the speed to keep a safe gap. So our target is minimum gap is 20 cm and the stop gap is 10 cm, which means when our car is too near the car in front and within 10 cm, our car will stop until the gap over 10 cm. But if still within 20 cm, it will follow the speed of the car in front until over 20 cm. Our car will go through the max speed. The next one is our attractor. We chose two TTDC motor as our attractor because the adequate for follow gap demo and also its low current fits the L29N and the BLC cells. And then for the mechanical part, our car was designed less or equal 1.5 kg. This is because it can keep inertia low enough for 10 cm stop within 1 second. For the motor driver part, we chose L29N as our motor driver because it's adequate for 2 ampere per channel. And then for the power supply, we chose two BLC branded 18650 Lion cells with 6800 mAh because it can keep more than 25-minute runtime at 50% duty. The next one is sensor. We chose SC-SL04 as our ultrasonic sensor because it can have a RAM spec cover our stop gap. And the last one is our control hardware. We chose ESP32 because it provides the Wi-Fi and Bluetooth for the telemetry and also got enough cycle for 100 Hz loop. And that's all for the design specification.
Next, I will continue with the system modeling, which is the transfer function. We begin by defining the key variables such as the distance between the two cars is denoted as dt, the desired safe distance is derived, the distance error as EDT, and so on. The estimated parameters of the system are control force, which is 1.5, mass of the vehicle, which is 0.75, and the damping, which is 1.5. The host car's dynamic are modeled as a first-order system, while the lead vehicle speed as a disturbance. Next, we will continue to derive the transfer function of the blunt model based on the Newton's second law of motion, which is F equal to ma. Throughout the derivation, we will get the transfer function from control force to vehicle speed, which is 1 over ms plus b, where the m is mass, while the b is the damping or friction. After that, we simulate the open-loop step response in MATLAB, and here is the MATLAB code for simulation with mass equal to 0.75, damping or friction equal to 1.5, and the force equal to 1.5. Here is the open-loop step response. However, this open-loop response was not ideal. The system had a slow rise time, slow setting time, and was not robust against disturbance. So, we need to design a PID controller to improve system performance. A PID controller helps solve three problems. The first one is the proportional KP, which is used to correct the error based on current difference. The second one is integral KI, which is used to eliminate the steady-state error over time. And the last one is the derivative KD, which is used to predict the future trend and smooth the response. And our performance specification will setting time less than 1.5 seconds, overshoot under 10%, and steady-state error is 0. After determining the performance specification, we will continue to find the PID controller transfer function. And here is the general form of a PID controller in the Laplace domain. And for the step 4 is we will continue to derive the open-loop transfer function of the PID controller. For the step 5, we continue to find the closed-loop transfer function in order to find the closed-loop step response of the PID controller. And the below here is the melee code simulation, and the value of KP, KI, KD are determined through a trial and error process. Obviously, after applying the PID controller, the rise time improved from 1.1 second to 0.693 second, and the setting time improved from 1.96 second to 1.22 second. The overshoot was minimal, around 0.02%, and the steady state error is 0. And this result fully met our design criteria. Next, we will continue with the Simulink system structure. Here is the Simulink block diagram. The system includes two controllers, which are distance and velocity PID controller. Then it got summation block that combines their output. After that, it will go to the vehicle dynamic transfer function based on mass 0.75 and damping 1.5. Lastly, it got a feedback loop that uses actual distance and speed to adjust control. And the diagram below here shows the values of KP, KI, and KD of the PID controller.
This slide shows the core components of our cruise control system. There are three main inputs: dref, the desired safe distance set to 0.2 meters; dt, the actual distance from the lead car measured by the ultrasonic sensor; vref, the desired speed which can be adjusted based on distance error. The systems use two PID controllers. The distance controller compares dref and dt to calculate the error and adjust the speed set point. The velocity controller then compares vref with the actual speed vt and generates the control force ut to drive the motor. This calculated control setup lets us handle both position and speed precisely, ensuring smooth, stable, and responsive behavior even in changing conditions. Now, let's look at how the system translates control signals into motions. First, the outputs from the distance and velocity PID controllers are summed to form a total control effort, UT. This represents the force applied to the vehicle. This signal is then sent to the vehicle dynamic block, which models how the vehicle responds. The system is represented by a first-order transfer function, where Gs equal to 1 over 0.75 s plus 1.5, where 0.75 kg is the mass and 1.5 Newton second per meter is the damping coefficient. The output of this block is the actual vehicle speed Vt. This value is continuously feedback to both PID loops, allowing the system to make real-time corrections. So in simple terms, the controller acts as the brain, Ut is the decision, and the dynamic block is the body responding, making sure everything stays smooth and accurate.
This is the response curve of actual measured distance from sensor, and it's generated by the signal editor, and the actual speed of horsepower versus time. For this graph explanation, let me turn to the next page to continue. The test runs 45 seconds and shows the three key moments. From 0 to 15 seconds, the car starts too far behind the lead car, which is 0.3 meter, and it speeds up to about 1.1 milli per second. Closes the gap, then settles at 1 milli per second once the distance hits the target of 0.2 meter. At 15 seconds, the lead car brakes hard, and the gap shrinks to 0.1 meter. Our car cuts speed right away, avoid a crash, and holds to have a safe gap. When the lead car moves off again, the gap will grow, and from 30 to 45 seconds, the gap reached 0.25 meter. So the system lets the car speed up slightly to 1.05 milli per second, and then slow back to 1 milli per second as the gap returns to 0.2 meter. Throughout the distance stay between 0.1 meter and 0.3 meter, and speed change are smooth, providing the controller works.
This block diagram shows how our system works as a whole. The ultrasonic sensor measures the distance ahead and sends it to the ESP32, which runs a PID controller to calculate the data speed. The output is sent as PWM signals to the L298N motor driver, which controls the DC motor to adjust the car's movement. Mechanically, the car uses a lightweight chassis under 1.5 kg, allowing fast and safe responses. We chose this design because it offers stable control with PID, accurate sensing, and an efficient cascade control structure that handles both speed and distance well. It's a simple, safe, and effective architecture for a scaled-up SEC system.
Now, I want to present about the circuit diagram of our cruise control auto car. So for left-hand side is our schematic diagram, and the table and right-hand side show the pin connection of ESP32. We can see from both diagrams the pin connection, like pin 25 and 26 is for the triangle and echo of ultrasonic sensor. Pin 0, 2, and 4 show right motor control, and pin 5, 16, and 17 show the left motor control. And for the VCC, we connect 5 volt is because the ultrasonic sensor require 5 volt to start up, and the ground we connected to ground. So that's all for the circuit diagram. Okay, so for now is the real connection for our cruise control auto car. So from the diagram, we can see the connection and with the one ultrasonic sensor, one L29AM motor driver, two TTDC motor, the power supply, which is two BLC brand battery with 6800 mAh, and also the controller hardware, which is the ESP32.
Our systems uses the HCSR04 ultrasonic sensor mounted at the front of the vehicle to measure distance in real time. It works by sending out a pulse and measuring the time it takes to receive the echo, using the formula distance equal to the speed of sound multiplied by time over 2. The key specs include 5-volt operating voltage, 2 to 400 cm range, the high accuracy and 15-degree detection angle. The sensor sends distance data to the ESP32, allowing the controller to adjust speed instantly. In short, the ultrasonic sensor acts as the eyes of our vehicle. Without it, the SCC system couldn't function effectively.
Now is the actuator part. For our project, the cruise control autocar, the actuator is 2 TTDC motor. By using the dynamic equation of the DC motor, we can derive an equation that shows how input voltage can change to the output speed. And the diagram is show the circuit inside the DC motor. So now let's turn to the equation part. So the final equation, output speed input VA, is combine the equation from the electrical part and also for the mechanical part. So the final equation we get is KT per LA plus SLA times B plus SJ plus KT KE plus F. So this DC motor block diagram is come from the dynamic equation that we state just now, and is from the electrical part and also the mechanical part. So we can see all of the element is go through into the block diagram for us to easily understand. After getting know the mathematical model of DC motor, we should know its specification. So for DC motor, it got several specification. For example, like each driver IC is L29N, and its motor supply is 5 until 35 watt, and the logic current is 0 until 36 milliampere, and maybe the max current per channel is 2 ampere per peak. And one more interesting for its specification is its protection, because it got clamp diode on each half bridge and have a thermal shutdown in IC. Okay, so now is the electronic hardware part, and for the electronic hardware, we choose ESP32. And why we choose ESP32? The first is because it is a low-power dual-core 22-bit microcontroller with the built-in Wi-Fi and Bluetooth connection. Besides, for the input and output part, it got up to 48 GPIOs, and also it integrated the 18-bit ADC, 8-bit DAC, capacitive touch, and also the temperature sensor. And the last one is its development. It because it's supported by the expressive ESP IDF, include the C and C++, the Arduino Core, the MicroPython, and the Platform IO. So that's all why we choose the ESP32. Okay, now is the second electronic hardware. So the motor driver we choose is L29AN. And why we choose this? So the first one is because it got the dual HV driver IC for 2 DC motors or 1 bipolar stepler motor. Besides, it can drive up to 2 ampere continuous per channel, and we already say just now the TT DC motor is got the peak of 2 ampere. And the last one is because it controlled via the simple high and low signal from the microcontroller. It means for us it's simple to coding, and that's all for the electronic hardware part.
Our code runs on the ESP32 and uses tune KP, KI, and KT values from trial and error for stable control. The ultrasonic sensor calculates distance using distance equal to times multiplied by speed of sound divided by 2. If the car gets too close, under 0.1 meter, it slows down or stops. Otherwise, the PIT adjusts speed based on the gap. This keeps the car responsive and safe in real time. In our code, the motor behavior changes based on distance. If the distance is more than 0.3 meters, the car runs at the preset speed. If it's between 0.1 and 0.3 meters, it measures the speed of the lead car. If it's below 0.1 meters, the car slows down or stops. We also fine-tune each motor PWM to ensure the cars move in a straight line. Here's a short demo of our car in action, following a lead vehicle. When the lead car moves away, our car speeds up. As it nears the 0.2 meter target, it adjusts and maintains distance. If the lead car slows down suddenly, our car quickly reduces speed to a fraction. This shows the PIT controller work effectively, responding in real time with no motion or delay. You can watch the full video at the link below. Overall, the demo confirms that our ATC system performs well not only in simulations but also in real-world conditions.
Here are the reference lists that we refer through our whole project. That's all from us from Group 5. Thank you for listening.